So our primary focus today is going to be on rate laws. And rate laws are going to be how we focus on the impact of concentration on reaction rate. And so we'll get into more detail about kind of the nuts and bolts of a rate law as we go on today. But just understand that when we talk about rate laws, what we are talking about is the relationship between the concentration of a substance and how fast that reaction goes. And so one of the ways that we can monitor that, and we saw this yesterday, if we're looking at those average rates of disappearance for the reactants, we noted that at the very beginning of the reaction, the rate of change was much more significant than in the middle of the reaction, or certainly at the end of the reaction. It was that relationship, it was that observation that we noted that indicated to us why we needed to measure initial rates as opposed to rates measured at some arbitrary time after the fact. Because as the reaction tails off, eventually they all get to this stage, and they all are reacting relatively slowly because there's just not a whole lot of reactant there. Now we can rationalize this. This is about collisions again. The more reactants there are, the more collisions there are going to be. From a sheer probability standpoint, the more collisions you have, the more likely one of those collisions is going to be effective. But we need to look at this a little bit more precisely. So we're going to dig deeper here a little bit. And that's where this idea of a rate law comes in. A rate law is a mathematical indication of what the effective concentration will be on that reaction speed. And there are two methods that we can use to determine rate laws. One of them is something called the method of initial rates. The method of initial rates is actually what we are going to be focusing on in lab this afternoon. We'll be measuring how fast or slow a reaction proceeds based upon a variety of different factors. And we'll be using a variant of the method of initial rates to look at the orders of reaction for all the reacting species to help us determine that rate law. We can also determine rate laws graphically. This is called the integrated rate method. And what that involves is we monitor the concentration of a reactant, or we monitor the concentration of a product over time, and we use the rate of appearance or disappearance of that reactant graphically to determine our rate law. And there are some mathematical techniques that go into that. And if you peek ahead into the syllabus for the lab a little bit, what you'll see there is on Tuesday, we will be doing a lab that involves this methodology, and it also is going to be the subject of our first formal report in laboratory. So let's kind of cover the basics here. Let's say that we have a chemical reaction. We've got reactant A reacting with B to form products C and D. The reactant A and B are our reactants, C and D are our products. The rate of the reaction can be determined by looking at the concentration of that reactant A and the concentration of that reactant B. But there's some other letters in there that we need to kind of work our way around and through. One of these is K. K, lowercase k, uppercase K, in physics and chemistry, that usually indicates the presence of a constant. And this is one of those kinds of constants. The constant here is something called the rate constant. The rate constant kind of helps us to connect the dots between concentration and rate. And so the units of K have a whole lot to do with what A and B are. Not in terms of their chemical substance, but in terms of what those exponents are in that rate law. Because in the end, we're going to multiply K, A, and B together, and it's going to give us a rate that is in molar per second. Just like the rates that we were looking at yesterday. We're all molar per second. The rate constant is going to give us that relationship. Now, the thing about the rate constant is that it is a temperature-dependent constant. So its value at 200 Kelvin is going to be different than its value at 300 Kelvin or 700 Kelvin. And the main reason for that is we know that there is a temperature dependence to reactions. They're going to go faster at high temperatures and slower at low temperatures. That's all that collision theory stuff coming up again. For A and B, we're going to look at their initial concentrations here. So right when I mix everything together, what was the concentration of that reactant and the other reactant? Now, if I'm dealing with solutions, if I'm dealing with gases, where I'm looking at quantities that are usually on the molar scale, I have to understand that a lot of times when I mix them together, they're going to dilute each other. So we have to kind of consider that. When we're calculating those initial concentrations. The exponents here, M and N, these are what we refer to as the orders of the reaction. And really what they are helping us to look at is the overall impact of A and B on the reaction itself. Most often, the values of M and N are small whole number integers, most commonly 0, 1, and 2. Now, there are other values possible for these. It's possible to have a negative order. It's possible to have a fractional order. But for the most part, we are going to avoid those in this class because to get to those, that requires a pretty heady understanding of kinetics. That's something that you would explore in a physical chemistry course, a 300, 400 level junior, senior chemistry major kind of course, not here. So I'm not saying that you won't find examples. There might be a couple that filter their way through the homework because I don't screen those quite as closely. And a lot of them do use random number generators, and I just don't know what is going to pop out of any of them. So I'll teach you some ways to do those calculations, and if it happens to come up fractional, just know that that's possible. But as far as a quiz or an exam is concerned, you're not going to see fractional or negative terms. Again, that's out beyond us a little bit. So what do those orders actually mean? Well, what we're getting here in order is a relationship between the concentration of an individual reactant and the speed of reaction. And so what's kind of mind-blowing about this is that in a given chemical reaction, different reactants can have different impacts on the speed of the reaction itself. And that's kind of mind-blowing to think about, because what that says is, let's say I have a reaction between two substances. Well, I know from a general standpoint that if I raise the concentration, that should raise the reaction rate. But what this is telling me is it's actually possible that I can raise the concentration all I want for one of those reactants, and it won't do a thing to the reaction. Or I can raise one and it has a super big impact, and raise another one and it doesn't have that much of an impact at all. So again, keeping with these ideas, zero order would mean that we have the exponent equal to 0. Zero order reactants have no effect on the speed of the reaction. So I can raise their concentration all I want. It's not going to increase the rate of reaction. Now, keep in mind, we still have to have it there. It's part of the reaction. Take it away, it's just like a limiting reactant. If I don't have anything to react with, reaction stops. But in terms of speed, I can change it to whatever I want it to be. It's not going to change how fast the reaction goes. If the reaction is first order, what we're going to see is a linear impact on speed. I double the concentration of that reactant, the reaction rate doubles. I triple the concentration, the rate triples. I cut the concentration down by a third, the rate goes down by a third as well. And for second order, where the exponent is equal to 2, well, that's a squaring effect. So it's going to have what looks like an exponential effect on the reaction speed. Double the concentration, reaction speed goes up by 4. Triple the concentration, reaction speed goes up by 9. Increase concentration by a factor of 10, reaction increases by a factor of 100, 10 squared. So each individual reactant is going to have its own reaction order. And again, usually it's 0, 1, or 2. To discuss the overall order of the reaction, I need to add together all of those exponents in the rate law. So if I have a rate law that says, okay, reactant A is first order and reactant B is second order, the overall order would be first plus second, be third order overall. And so if I globally doubled everything, it would increase the rate by 8, 2 cubed. Because I would get a doubling effect from reactant 1 and a quadrupling effect from reactant 2. And 4 times 2 is 8. This is a really important point right here. We need to understand that our reaction order has absolutely nothing to do with our coefficients. Absolutely nothing to do with our coefficients. If a rate law happens to match the stoichiometry like it does on the bottom, that is kind of a coincidence. Now, when we talk about reaction mechanisms at the end of this, so tomorrow, we can actually talk about these kinds of reactions as being elementary reactions, meaning that they occur in a single step as opposed to over a series of steps. But for the most part, what we need to notice there's no relationship between the order of reaction and the stoichiometry of that reaction. So we can kind of put that one away. We have to find our reaction orders experimentally, not by the chemical equation. So this sets up for us something called the method of initial rates. Again, the method of initial rates, this is going to be the style of analysis that we are going to be doing this afternoon in our hydrogen peroxide lab. We use this method when we see instantaneous initial rates given to us. Usually in problem-based terms, that means we usually are going to be given some kind of a table. So if you're scanning through your problems and you get a table that looks like this, where it's got a whole bunch of columns and a whole bunch of rows, this is an initial rates problem usually. Because what you'll find in those columns are words like concentration of this, concentration of that, concentration of a third reactant, rate of reaction, and all those little numbers underneath are going to change just slightly. And what your task will be is determining the rate law and probably the value of the rate constant based on the numbers in that table. Now, there are two ways that you can go about doing this. The first one is the easier of the two. I call it the inspection isolation method. What you do is you pick out a couple of those reaction runs and you try to look for things held constant. Okay, so I'm looking at reactant A and reactant B and the rate of reaction. So to figure out what's going on with A, I'm going to look at reactant B and try to find two conditions where reactant B is the same, so I can compare reactant A directly to the rate. The second method, the algebraic logarithmic method, if you read through the discussion in your lab for today, it talks a lot about this secondary method. There's a lot of stuff in there about x's and logarithms and a whole bunch of other stuff. That's the logarithmic method. If we can't isolate, that's the method that we have to use. And it's a little bit more involved. You've got to do some algebra. You've got to do some comparing. You've got to do some calculations. Do it enough times, you get used to it. But it does require a good deal of practice to get used to. So let's take a look at this first example here. Use the data below to determine the rate law for the reaction BF3 reacting with ammonia to make the adduct compound of the two. Well, here I see I have enough reaction runs that I can probably just use the isolation method. Because I can see, okay, experiment 1 and 2, my boron trifluoride's held constant, my ammonia is not. And so I can compare them directly here. Now, from an inspection standpoint, I can look at this one and say, okay, the relationship between reaction 1 and reaction 2 appears to be 1/2. Concentration of ammonia in number 2 is half of the concentration in reaction 1. And the rate also went down by 1/2 as well. So if those are my guidelines for 0 order, 1st order, and 2nd order, which one is this most alike? Yeah, it's 1st order. Why is it 1st order? Well, we saw a change in the concentration and a similar change in the rate. Now, if you're thinking, well, that's 0 order, nothing changed, you're not thinking about 0 order correctly. If this was 0 order, we would see that the initial rate didn't move. It would have still been 0.213, regardless of what happened to the ammonia. So what we can write here, ammonia is 1st order. That degree sign there is an indication of order. It's an ordinal symbol. So ammonia is 1st order. Now we can look for other places. So we figured out ammonia. Ammonia is 1st order. Let's look at other places and see if we can find a place where ammonia is isolated. And we can see, okay, these last 3 reaction runs all have the same concentration of ammonia. Let's see if we can find 2 that are easy to compare. Well, if we look at reaction 4 and 5, we can see that ammonia has been held constant. We've got the same 1/2 occurring for boron trifluoride. And the rate has gone down by 1/2 as well. And so the same logic would apply here. 1/2 of one, 1/2 of the other. We're talking about a linear relationship between the two. Boron trifluoride is also 1st order. So to determine the rate law, all I need to do is, these are both of my reactants, I need to put them in that context. Rate, which I'm just going to abbreviate as capital R here, is equal to the rate constant, K, lowercase k, multiplied by the concentration of boron trifluoride to the first power, multiplied by the concentration of ammonia, also to the first power. That's my rate law. My rate law is first order in boron trifluoride, first order in ammonia, and second order overall. Again, to find the overall order, all I do is add together those exponents. All right, any questions with this first example? So this is the isolation method. If you've got lots of reaction runs, if your experimental design has been sound, meaning you actually put some thought into it, isolation is usually the easiest way to go. Any questions? Now, this is another example where we can use the isolation method, but just for illustrative purposes, I'm going to show you the logarithmic method just so that you know how to use it when the time comes to use it. So in this reaction, we are looking at nitrogen and oxygen reacting to make nitrogen monoxide. We want to find the reaction order and the rate constant. Now to do this, what we're going to need to set up is a pair of rate laws, and we're going to compare them to each other. So R1, we're going to look at experiment 1 here, is equal to K1 times the concentration of nitrogen 1 to the power M times the concentration of oxygen, condition 1, power N. R2 is going to be equal to K2 times the concentration of nitrogen at condition 2 to the power M, oxygen at condition 2 to the power N. Now, luckily, we have numbers to associate with each of these. So it's actually not as bad or gray as it looks. The R's, we can put in these initial rates. So instead of looking at this as R1 is equal to K1, N2, M, and so on, we can put numbers to this, and this will actually help us a lot. So R1, 701 molar per second is equal to K times the concentration 0.040 to the power M times 0.020 molar to the power N. And the second one, 496 molar per second is equal to K times the concentration of 0.040 to the M, 0.020 to the N. Or sorry, got ahead of myself there. 0.010 to the N. Well, all that I need to do is I'm going to divide these terms into each other. Yeah, the concentration M. Yeah. Yeah, so these should have concentration values in them as well. I left it out for reasons that will become hopefully a little bit obvious here in a second. So on this side of the equal sign, I've got 701 divided by 496. The molars per second cancel out. The units are the same on both sides. 701 divided by 496 is 1.41. Now on the right-hand side, since I'm at the same temperature, my rate constants are going to be the same for reaction 1 and reaction 2. So those cancel out. 0.04 to the M, also the same, cancels out. All that is left on the right-hand side of this equation is 0.020 to the N divided by 0.010 to the N. If I use my rule of exponents here, what I have is 0.020 molar over 0.010 molar to the N power, canceling out the molarities that are common inside. Doing the division, 0.02 divided by 0.01 is 2. So here we have 2 to the N power. Now, in this particular circumstance, it's kind of a blessing we did it this way, because off the top of my head, I can't think of any exponents, 0, 1, or 2, that are going to solve that particular problem. So what do? Well, this is where the logarithmic part comes in. To get this exponent out, we need to go log of 1.41 is equal to log of 2 to the N. Log of an exponential term turns this into N times the log of 2. And so that means that N is equal to the log of 1.41 divided by the log of 2. Which is equal to 0.5. So, like I said, this won't show up on a quiz or an exam for you, but this is an example of a fractional order. So we're looking at oxygen in this case. Oxygen's order is 1/2. So now we need to do the similar kind of thing for nitrogen. Luckily, this one should be a little bit easier to do by inspection. Reactions 2 and 3, we can see that the oxygen has been held constant. Nitrogen has gone down by a quarter. 496 divided by 124. This is also a 1/4 change. So that means that the nitrogen is first order. So as far as rate law is concerned, the rate of our reaction is equal to K times the concentration of nitrogen to the first and the concentration of oxygen to the 1/2 power. That means that the overall reaction order is 1.5. To find the value of the rate constant, we're going to have to break out a whiteboard here. Anytime you're asked to find the value of a rate constant, the easiest thing to do is if we go back to the drawing board of our initial kind of blanket rate law. Now inserting the proper values. We can insert our values from any of the experimental runs in and basically solve for K. So we had 701 molar per second as the rate. K is what we're trying to find. We have 0.040 molar to the first power as our nitrogen, 0.020 molar to the 1/2 power as our oxygen concentration. If I combine the 2 molar terms and multiply, 0.04 times 0.02 to the 1/2 power. 1/2 power is square root. So I would get 5.7 times 10 to the -3rd molar to the 3/2 power. 3/2 because I have molar to the first plus molar to the 1/2. If I divide each side by 5.7 times 10 to the -3rd molar to the 3/2. I'll cancel out this term. 701 divided by 5.7 times 10 to the -3rd gives me a value to 2 significant figures, 12,000. Unit on this one's going to be really funny. I've got molar to the first divided by molar to the 3/2. 1 minus 3/2 would be -1/2. So molar to the -1/2. Seconds in the denominator, -1. So this would be the value of my rate constant. 12,000 times molar to the negative half per second is my constant value. Right. As far as examples go in terms of using this methodology, this is about as complicated as they get. It's getting into half powers. The only other way that would be, maybe more complicated is a negative power, but you're not going to, again, you would find that negative power using this logarithmic method. So if you get to an isolation point and you can't quite figure out what it is that you need to do, the logarithmic method is the way to go. And so even if you don't have you can go all the way through this process here. If you had started with isolation and said, okay, this is held constant, this is a doubling effect, 701 divided by 496 is 1.41, you'd still end up at the same spot where we were at the end, where you're going, okay, 2x versus 1.41x, it's definitely a change, so it's not zero order. It's not a linear change. It's not an exponential change. It's not an integer change. How do I rectify that? Well, I go down to this. I can kind of skip to the bottom here. Log of 1.41 is equal to x log of 2. Set them equal to each other, and you end up with the half power. All right, any questions on this one? Okay, so we're going to go on break here. I'm going to leave this one up during the break, 15 minutes, so we will come back at 9:20, and we will start with this question. So feel free to approach it however you want, but get your answer in before 9:20, and then we'll talk about it then.